Hi everyone, so today I have a very fun question for you, and in this video we're going to be looking at how we can use Taylor series expansion to solve certain nice inequalities. So yeah, let's get started. This is a problem number B3 from the Putnam exam in 2002, and in this video we're going to be looking at Taylor and Maclaurin series, a brief introduction to what they are. After that we're going to use Taylor series to solve certain inequalities. Then we have some book sessions for college mathematics, and at the end, a similar challenging problem.
This video is sponsored by Cheenta.com. Since 2010, Cheenta has trained thousands of students from all around the world in mathematical Olympiads, physics Olympiads, computer science and informatics Olympiads, ISI CMI entrances, and research projects for school and college students.
Okay, so what do we need to do? So we need to prove that for all integers n greater than 1, essentially for all natural numbers greater than 1, we need to prove that it satisfies this given inequality. And it looks something weird, right? It looks something extremely non-trivial. So how can we proceed with this? So maybe let's just manipulate the terms a little bit here and there and see if we can maybe form an expression that is a little bit easier to deal with, a little bit simple. So, my first observation is that, the limit as n tends to infinity of 1 minus 1 by n raised to power n is actually 1 by e. And this is actually quite fascinating. So, it might have something to do with the problem, maybe, who knows. So, let's see how we can proceed. So, we have this given inequality, right? This weird looking expression over here. What I'm going to do is I'm just going to right away subtract 1 by e from both sides to remove this term over here. So we will have 1 by 2ne minus 1 by e is less than this quantity over here. And that's less than 1 by ne minus 1 by e. And because I have this negative over here, we really don't like dealing with negatives. So let's just multiply every term by a negative. And the sign of the inequality was obviously flip in that scenario, right? So we get 1 by e minus 1 by 2ne that is greater than this quantity in the middle, which is again greater than 1 by e minus 1 by ne. So it is definitely starting to make a lot more sense. Now what I'm going to do is maybe to simplify it a little further. We really don't like this quantity's e in the denominator. So we multiply by e on all of these terms, right? So we get 1 minus 1 by 2n that is greater than e times this quantity in the middle, which is greater than 1 minus 1 by n. I think this expression is probably looking a little better than what we started with, right? So we've probably made certain progress over here. How can we make more progress? Well, you can pretty much see that using logs over here can be help us because ln e is 1 and this entire power thing can get reduced in a way. So if we just take logs over here, the log of 1 minus 1 by 2n will be greater than, and just maybe using certain properties of logs, I can simplify this down a little bit. So this becomes n log 1 minus 1 by n, which is greater than log of 1 minus 1 by n. And this is a really nice thing actually, and this essentially works because log is an increasing function. So if x1 is greater than x2, that essentially means that log of x1 will be greater than log of x2. Obviously, we are assuming that the base is greater than 1, and here it is because you assume the base to be e. We're dealing with natural logs over here. Okay, great. Well, what next? How can we maybe proceed further? But I think here it's good to discuss a little bit of the Taylor series. So what's the Taylor series? So the Taylor series is nothing but a way to represent a particular function in the form of certain polynomials. So for example, if you ever thought maybe e raised to power x or ln x or whatever this function, sine x, cosine x, these functions can actually be approximated in the form of polynomials. So e raised to power x can actually be written as 1 plus x squared by 2 factorial plus x cubed by 3 factorial plus x raised to power 4 by 4 factorial, and so on and so forth. This just goes on and on and on, right? So this expansion in a way of a function into its polynomials is what we call the Taylor series. And what's the formula for this? This is a very standard formula. So you can find out the Taylor series for any function you want. So for any function f, the Taylor series is given by f of x equal to f of a plus f prime a times x minus a divided by 1 factorial, which is 1, plus the double derivative of x equal to a times x minus a whole squared divided by 2 factorial. And you can see this pattern is kind of repeating. Then we'll have a triple derivative at x equals to a times x minus a whole cubed divided by 3 factorial. And again, this also keeps on repeating on and on and on and on. This is sort of weird sort of expression that keeps on repeating on and on. And if I just plug in at a is equal to 0, if I just calculate a is equal to 0, we get the Maclaurin series, right? So to be a little bit more specific, this thing that we've written over here, the expansion for e raised to x, is actually the Maclaurin series. We're calculating the Taylor series about a is equal to 0, which is the center. So, well, how is that relevant to our problem? So you see, I have this log of a certain quantity on both sides. And more precisely, I have a log of 1 minus some quantity. So if you're kind of getting the idea of log of 1 minus something, over here that x is 1 by 2n, over here that x is 1 by n. So it's just differing, but essentially we have log of 1 minus x and some other terms here and there just for good measure, right? So the natural question that I ask, does log of 1 minus x have a easy to deal with expansion? Does it have an easy to deal with Maclaurin series expansion? And yes, it does. Log of 1 minus x can in fact be approximated as negative x squared by 2, negative x cubed by 3, negative x raised to power 4 by 4, and so on and so forth. This goes on and on, right? So the negative of logarithm 1 minus x is actually x plus x squared by 2 plus x cubed by 3 plus x raised to power 4 by 4, and so on and so forth. So maybe if I just take this given expression that I had, what did I have with me right now? I had log of 1 minus 1 by 2n, which was greater than 1 plus n log 1 minus 1 by n, which was greater than log of 1 minus 1 by n. If I maybe multiply by negative 1 on both sides, I'll get something similar to this log 1 minus x that we have over here. So multiply with negative 1 on all sides, and obviously again the sign of the inequality would flip. So we get negative logarithm 1 minus 1 by 2n, which is less than negative 1 negative n log 1 minus 1 by n, which is less than negative log 1 minus 1 by n. And let me just maybe write the Taylor series again over here. Negative log 1 minus x is x plus x squared by 2 plus x cubed by 3, and so on and so forth. So let me just analyze the terms one by one. So for example, if I maybe try to write the Taylor series expansion of negative log 1 minus 1 by 2 raised to power n, or 1 by 2n, right? You can try this by yourself, but I'm more interested in the kth term, right? In the kth term. So what was the kth term? Well, what's the kth term for this log 1 minus x? It's nothing but x raised to power k by k, right? Because you put k is equal to 1, you get x by 1, which is x. You put k is equal to 2, you get x squared by 2. The kth term is very clearly x raised to power k by k. So when you have this expansion over here, what would be the kth term over here? It would be 1 by 2n raised to the power k divided by k. Very simple, right? Because x over here is taking the role of 1 by 2n. So basically just replacing that, right? So the kth term over here for me would be nothing but 1 by 2n raised to the power k times k, which is nothing but 1 by 2 raised to the power k times n raised to the power k, right? So effectively I can write this thing as over here, what we have over here, right? So the kth term of its expansion essentially. Okay, great. Now similarly, using kind of a similar idea, can I maybe write the kth term of this thing? So remember, the kth term was x raised to the power k by k. And over here, x is playing the role of 1 by n. So what would it be over here? You would have 1 by n raised to the power k divided by k, which is very simply, the kth term is 1 by n raised to the power k times k. And we again coming on to the middle part, right? We have the middle portion as well to deal with, right? This middle thing over here, which is kind of giving us all the problems in the world, right? So we have that negative 1, negative n log 1 minus 1 by n. If we just ignore this negative 1 over because it's really not doing much, just like a constant. And if I maybe just consider the kth term of this factor over here. So again, the kth term was x raised to the power k by k. Here x is acting as 1 by n. So what would the kth term? The kth term would be 1 by n raised to the power k by k. But then you have this n multiplied over here as well. So just multiply this by n. So all in all, what you would get is you'd get 1 by k times n raised to the power k minus 1. And I don't really like this k minus 1, so I can just change the base. I can just put this as k plus 1 times n raised to the power k. Essentially, when you have n raised to the power k, you will be multiplied with k plus 1 in the denominator. So what do we have? Maybe we just label this as number 1. Okay. Maybe let's just label this as number 2, what we had over here. And maybe just label the third thing that we had figured out. Where did it go? It was this, number 3. So what do we have from these three quantities? We essentially now have reduced the inequality to proving this simple statement. Proving this simple inequality, right? Proving this simple inequality. Well, this one thing comes in the middle. This becomes k plus 1 times n raised to the power k. This 2 thing comes on the equation number 2 comes on the right hand side, which is 1 by n raised to the power k times k. And equation number 3, which we had taken first, was the one for this, right? So it obviously comes on the left hand side. 1 by 2 raised to the power k times n raised to the power k times k, right? That's what we had over here. Now we just need to prove this inequality. So what have we done till now? We've reduced our original inequality, which was like you had the Euler's number, you had a lot of other stuff, you had some exponential things over there, you had the small e in the denominator and all of that stuff. We essentially reduced that to things that we can comfortably deal with this, right? Fractions and effectively natural numbers. Easy to compare terms like this, you know. So if I maybe prove that this inequality holds, that means everything that I written before this, the above said inequality, this inequality is also true. And if this inequality is true, that means the original inequality is also true. So that means the problem is very much reduced to just solving this inequality. And this is actually very easy to prove that this holds, because you see that k plus 1 is greater than k. N raised to the power k is common everywhere. So you can just kind of ignore that. It does not matter. It's not affecting inequality anyways. N raised to the power k is a positive quantity. It's not affecting the inequality in any way whatsoever. So let's just ignore that. Okay. So you have this k plus 1 quantity over here in the denominator, and you have this k over here, k plus 1 over here. So you know that k plus 1 is greater than k. So that approximately means that 1 by k plus 1 is less than 1 by k. Right? And then you just multiply by n raised to the power k. As simple as that. So this inequality holds good. Right? Now let's look at maybe the other inequality. Let's maybe analyze the first and the third term. So let's say if this is term 1, this is term 2, this is term 3. So we said that 2, 3 holds true. Let's maybe consider 1 and 3, right? Let's maybe consider 1 and 3. Well, what is common between 1 and 3? This n raised to the power k term is obviously common. Here you have k, but then you have k as well, but then you have another quantity 2 raised to the power k. So it's obvious that 2 raised to the power k times n raised to the power k times k will be greater than n raised to the power k times k, which essentially means that 1 by this quantity, n raised to the power k times k, will be less than this quantity on the right hand side. And therefore the quantity on the right hand side, 1 by that quantity is greater. So therefore this inequality also holds. So we've proved that 2 and 3 hold, 1 and 3 hold. So all it suffices now is to prove that this middle thing, 1 and 2, also holds. And if you've proven that, that's it, we're done. Now let's just analyze that. What do we have over here? We have k plus 1 raised to the power, let me just write it like this. We have k plus 1 raised to the power, or k plus 1 multiplied by n raised to the power k. Yeah, k plus 1 multiplied by n raised to the power k. And over here we have 2 raised to the power k times n raised to the power k times k. And we need to prove that this inequality obviously holds true. Maybe let's just see. You don't know what the sign is, right? So n raised to the power k, n raised to the power k is common on both sides. It's not making any difference. Might as well forget about it. Might as well forget about it. Okay, what next? Well, I think it's easy to see that 2 raised to the power k is an exponential function. And when you multiply this by this k term, it is obviously going to be greater than k plus 1 for all k greater than 1. I think it's pretty easy to see that. Right? For example, at k is equal to 2, it holds true. Right? And this can be easily proved by induction as well. But okay, anyways, so it's pretty easy to see just by observation that this quantity is true. Now, all I really need to do is multiply by n raised to the power k. Again, n raised to the power k is a positive quantity, so the sign of the inequality remains the same. So 1 by this quantity, 2 raised to the power k times n raised to the power k times k, is less than 1 by this quantity, k plus 1 times n raised to the power k, which is what we had to prove, right? This is essentially what we had to prove over here, right? 1 and 2, it was the same thing. We had to prove that this inequality actually holds good. and we've actually proven that it holds good. So we've proved that 2 is less than 3. We've then proved that 1 is less than 3, and then I've proved that 1 is less than 2. So that automatically means that 1 is less than 2 less than 3 is the true inequality essentially. So now that we have proved this reduced inequality, it means that the inequality that we had up top over here is also true. And if this inequality is true, that means the inequality given to us in the question is also true. And that's it. Hence proved. That's the end of the question. So yeah, I hope you learned something from that. And really what the takeaway is that probably one of the best problem solving techniques when it comes to solving inequalities like this of this form is by using some sort of power series expansion or the Taylor-Maclaurin series, and then try working with that. Okay, so moving on to some book sessions for college mathematics: Introduction to Real Analysis, Principles of Mathematical Analysis by Rudin, Calculus Volume 1 and Volume 2 by Apostle, Topology, Contemporary Abstract Algebra by Galian, Topics in Algebra by Herstein, Abstract Algebra by Dummett and Foote, and of course, Linear Algebra done right by Axler. Okay, so at the end we have a similar but challenging problem, and well, really for this question, it turns out that you do not need to use power series expansion, nor do you need to use any kind of Taylor series whatsoever. So maybe just try this in simple calculus techniques. Of course, it does involve calculus, but yeah, maybe try it out. It's probably not that hard. And if you're able to solve it or make any significant progress on it, let me know in the comment section. And until then, I'll see you in the next video. Thank you very much and bye-bye.
Cheenta programs are designed for students who are passionate about mathematics. And they are personalized with one-on-one training, individual evaluation, and remedial sessions. The reason Cheenta students are successful over the last 10 years because they are taught by mathematicians and real Olympiads from leading universities in India, United States, and Europe. Some of our students come back to teach at Cheenta from Oxford, Cambridge, Harvard, MIT, UCLA, ISI, CMI, IITs, TIFR, and IISc. For more information, visit cheenta.com.